Hello everybody, this is Professor Roman. Welcome to the 17th video in my video lecture series, An Introduction to Discrete Mathematics. Today we are going to look at partially ordered sets. As we've seen, equivalence relations are relations that are reflexive, symmetric, and transitive. If we replace symmetry by anti-symmetry, we get another extremely important type of binary relation called partial orders. And in this section, we're going to take a close look at the mathematical notion of order. The most common binary relation that's reflexive, anti-symmetric, and transitive is undoubtedly the usual order, denoted by the less than or equal to sign on the real numbers. Now, this order satisfies one additional property besides being reflexive, anti-symmetric, and transitive, namely, every pair of real numbers is comparable. So if x and y are real numbers, then either x is less than or equal to y, or y is less than or equal to x. But the general concept of order does not require this fourth property. And that's why we refer to it as a partial order, as opposed to a total order. And I'll go over these concepts again. So for example, set inclusion is reflexive, anti-symmetric, and transitive, and so it's a partial order. But set inclusion is not a total order, because it's not true that given any two subsets of a set, a universal set, one of those subsets has to be contained in the other. They can be entirely separate. For example, the set containing 3 and the set containing 5, neither one is a subset of the other. So here's the formal definition of partial order. A binary relation R on a non-empty set A, that would be the underlying set, is called a partial order if it's reflexive, anti-symmetric, and transitive. And I'm going to use these two symbols most of the time. They resemble the less than or equal to symbol. And frankly, in many books, they will just use the less than or equal to symbol. But since this is a beginning course and introduction to order, I'm going to choose slightly different symbols. And sometimes we'll be talking about two ordered sets at the same time, so I want two different symbols. A set P, if a set P has a partial order defined on it, then this ordered pair, P together with the order, the relation, the partial order, is known as a partially ordered set, or poset in short. Okay. And we would also say that P is partially ordered under this relation, or that the relation orders P. If we have a partially ordered set, borrowing from the case of the sort of the prototypical case of the real numbers with the usual order, we do say that if A and B belong to this arbitrary poset, and we write this, A is related to B under this order, we would say A is less than or equal to B. It's just such convenient terminology, even though A and B may not be any kind of numbers. They could be sets, they could be functions, they could be anything, frankly. But less than or equal to is the generic term that we would use here, A less than or equal to B. Okay. If we have a specific order in mind, like the subset relation, we would say A is a subset of B, of course. We use the specific language when it's available, but this is going to be our general language applicable to all posets. Okay, greater than or equal to also. If A is less than or equal to B, but A and B are different, we would write this or this, depending on the notation we're using, and say that A is strictly less than or simply just less than B. Okay. I should remark further about this ordered pair notation. Why do we need an ordered pair? Well, it's possible in general to define many partial orders on a given non-empty set. And each of these orders makes a different partially ordered set. Same underlying set, but different relation will be a different partial order. So it is customary to include the symbol that represents the order, and therefore use an ordered pair to emphasize both the underlying set and the order relation. Well, just as I say this, I have to also say it's customary for mathematicians to drop this formal notation. I try not to, but I do it sometimes, and simply refer to P as a partially ordered set. That's okay, provided it is crystal clear what the partial order is at the moment of the discussion. Okay. So if I said, let's consider the partial order of set inclusion, let P be a partially ordered set, you would know I'm talking about set inclusion. Okay. It's best to stick with the ordered pair notation so there's no confusion. We extend the notation a bit if I'm just going to say, as I read, if P is a poset. And if A, B, and C are elements of P, and A is less than or equal to B, and B is less than or equal to C, we would write that in a shorter version like that. And similarly for more than 3 elements. Okay. So here's an example. P is the set 1, 2, 3, ABC, and the relation here is defined this way. I've forgotten where I got this. I probably made it up. The first 2 rows ensure that this relation is reflexive. 1 less than or equal to 1, and so on, up to C less than or equal to C. And I'm going to leave it to you to check anti-symmetry and transitivity. It's a little work, but not serious. And so this is a partially ordered set under this particular relation. I'm not claiming this is useful, but it's just an example. We can change the relation. This is a different relation. It still has the first 2 rows in common with the previous one to make sure we have reflexivity, but this is also anti-symmetric and transitive, so P is a different partially ordered set under this relation. So the same underlying set, we have 2 different partial orders on it, each of which are probably equally useless. So the usual order on R, as we've discussed, is a partial order, and so this ordered pair is a poset, or you could say R is a poset under the usual order. Any subset of R, such as the integers or the rational numbers, or in fact any subset, inherits the same order structure. Okay. That's one of the nice things about order. Subsets automatically inherit the order relation. It's automatically a partial order on the subset. Okay. You may be familiar with vector spaces and subspaces. A subspace is not just a subset. It has to have closure under the operations that define a vector space. We don't have to worry about closure for partially ordered sets. The power set is ordered, partially ordered by set inclusion, so that's a pose set. Smaller than or equal to means subset of, and you would say subset of. The relation of divisibility is a partial order on the integers. As you know, it's denoted by a vertical bar, so this is the pose set. And in this pose set, less than or equal to means divides, and greater than or equal to means is divisible by. And so in this case, we say that Z is ordered by divisibility. If sigma is an alphabet and it is partially ordered by a less than or equal to, we can use that partial order to define another partial order on the set of words over the alphabet. And it's customary to use the same symbol, so we'll do that. The new partial order, the one on the words over sigma, is defined basically to be alphabetical order, where the alphabet order is determined by the original partial order on sigma, on the set of letters. Okay. So to compare two words, W and U, we first compare the first two letters, A1 and B1. If A1 is less than B1, then W is less than U. And similarly, if B1 is less than A1, then U is less than W. But if A1 and B1 are equal, we just move to the second pair of letters and do the same comparison. This is exactly what we would do to compare two words in the English language, for example. If we run out of letters in one word before we have run out on the other word, then the shorter word comes before the longer word in this order, alphabetical order. Okay. The term alphabetical order isn't generally used. It is referred to as lexicographic order or possibly dictionary order. Lexicographic order can be used to order the set R2 of points in the plane. All we need to do is think of an ordered pair, which represents a point in the plane, as a word. So drop the parentheses and the comma. It becomes just AB, and then we use lexicographic order. Okay. So for example, if we were comparing these two ordered pairs, these 2 points in the plane, because the x coordinate is smaller than in the first ordered pair than it is in the second, the ordered pair is less. And here we have the same first component. 3 is less than 4, however, so this ordered pair is less than this one. Now, associated to any poset, any partially ordered set, P with the less than or equal to symbol I've been using, we can associate another order relation on P written this way. So I dropped the underline here in this notation. A less than B if and only if A is less than or equal to B and not equal to B. Okay. This relation is called the strict order relation associated with the original partial order. The strict order relation is asymmetric and transitive. And therefore, by an earlier theorem, it's also irreflexive. And to see that the less than relation is asymmetric, one way to do it is to assume that A is less than B and B is less than A and produce a contradiction. Well, if A is less than B, it's less than or equal to B, and similarly, B is less than or equal to A, but the full relation is antisymmetric, which would imply that A equals B, which would contradict A less than B by definition. Here it is. They're not equal. So that's our contradiction. That's all we need. And we know that the less than relation is asymmetric. And I'm going to leave it for you to check transitivity. So here's a definition. A binary relation, and this would be read less than, on a set A is called a strict order if it's asymmetric and transitive. So associated with any partial order on a partially ordered set is a strict order, and it's defined this way. There's actually an equivalence between partial orders and strict orders, because if we start with a strict order, in other words, an asymmetric and transitive relation on a set, then we can define a partial order in this way: A less than or equal to B if and only if A is less than B or A is equal to B. So it's quite easy to pass back and forth between partial orders and strict orders. Sometimes one is more useful than the other. They're just different points of view for the same concept. At the beginning of this discussion, I mentioned the real numbers with the usual order, and I said that that relation had an additional fourth property, namely every pair of real numbers is comparable, but that, for example, for set inclusion, that property does not hold. It's really quite critical to relax that fourth property and not require it. Because if we always required comparability, we would lose a lot of important relations, like set inclusion, like divisibility. If, however, a partial order does have this property, then that's worth some special attention and some terminology. So let's begin with this definition. Let P be a partially ordered set. We say that two elements are comparable if either A is less than or equal to B or B is less than or equal to A. If not, then A and B would be said to be either incomparable or parallel. So, for example, in the relation of set inclusion on the power set of S, two subsets are comparable if and only if one is a subset of the other. So it's easy to produce examples of comparable and incomparable subsets. Two integers are comparable under divisibility if and only if one divides the other. So 6 divides 12, they're comparable. 6 does not divide 7, 7 does not divide 6, so they're incomparable or parallel. Now we come to a main definition. A partially ordered set in which every pair of elements is comparable is called a totally ordered set, or a linearly ordered set. And then the partial order would be referred to as a total order or a linear order. If sigma is an alphabet that's totally ordered by a relation, then lexicographic order on sigma star is also totally ordered. And I'll leave that for you to verify. The post set Z under divisibility is not totally ordered, and on the other hand, the post set Z with the usual order is totally ordered. So same set, same underlying set, but two different relations, one of which is totally ordered, the other which is not. This concept, covering, is quite important in the study of order. It describes the situation where two elements are as close as possible without being equal. So here's the definition. We have a partially ordered set. A and B are elements of the underlying set. Then we say that B covers A if two conditions hold. A is less than B, B is greater than A, and there are no elements between A and B. So if we have this, A less than or equal to C less than or equal to B, then C is either equal to A or it's equal to B. Nothing in between. In the case of a power set under set inclusion, what does it mean for B to cover A? It means that A is a subset of B, and B will have exactly one additional element that's not in A. So B will look like this. In the post set of real numbers under the usual order, no element covers another element. And that's because given A less than B, there are real numbers in between. In fact, infinitely many real numbers in between A and B. So there's no covering whatsoever in the real numbers, nor is there in the rational numbers. In the integers, yes. Rational numbers, no. Real numbers, no. We've already talked about the fact that if we have a finite underlying set, a relation can be described by a directed graph. When a binary relation is a partial order, we can use the covering concept to get a nice graphical picture. It's not a directed graph in quite the same sense. In a way it is, but let me describe what it would look like. So we start with a post set P. As before, we let the vertices of the graph represent the elements of P, but we place the vertices on different levels, and they're ordered horizontally, so level 1 is below level 2, which is below level 3. And we'd start by drawing a vertex, a point in the plane, at the same horizontal level, so along a horizontal line segment. Draw each vertex that is minimal in the sense there are no smaller elements in the post set. So we look for the smallest elements and we set those on the first line, horizontal line. Let's call that level 1. Then we scan the remaining elements of P, looking for elements that cover at least one of the level 1 elements. And we place those on a line segment above the level 1 vertices. That's level 2. Then we repeat the process, climbing to higher and higher levels, using the covering relation. Since we're assuming P is finite, we will eventually be finished with that process. Now, we connect two vertices with a straight line segment called an edge. We don't need an arc, so we don't have a direction, just a straight line segment if one of the vertices covers the other vertex. So that's going to connect two adjacent levels. Okay. And that resulting graph is called a Hasse diagram for the poset. And that may have been a little abstract, so let's take a look at some examples. Here is a poset I defined earlier. So the first step would be to find the smallest, what we call the minimal elements, elements for which there's nothing smaller. And I'll go into that detail a bit later. We'll talk about minimal and maximal elements. So 1 is a minimal element. There is nothing smaller than 1. Okay. 2 is not minimal because 1 is strictly less than 2. Okay. Even though I didn't use a strict less than sign, 1 is not equal to 2. And so 1 being less than or equal to 2 means 1 is less than 2. But A is minimal. A is, there's nothing smaller than A, nothing less than A. So here is my bottom level, level 1. It has a vertex labeled 1 and a vertex labeled A. I don't actually draw a horizontal line segment. That was just for descriptive purposes. Now we scan the list again, the elements of P, and we look for elements that cover either 1 or A. Well, 2 covers 1. 2 is bigger than or equal to 1, but there's nothing in between. So we place 2 on a second level, and we draw this edge that indicates a covering. B covers A in the same manner, so B goes on the second level. If B happened to cover 1, we would draw an edge between B and 1, but it doesn't. For the third level, we look for elements in P that cover the elements of the second level. And so after drawing all the edges, this is our Hasse diagram. Okay, this wasn't really that interesting in the sense that I just made this order relation up. So let's look at something more serious. Let P be the set 1, 2, 3 under set inclusion. Level 1 of the Hasse diagram will have the subsets of P for which there's nothing smaller. That's only the empty set. So level 1 here just has one vertex labeled with the empty set. Now, which subsets of P cover the empty set? They're the subsets that have one more element than the empty sets. In other words, the singleton subsets. So those are the sets containing 1 or 2 or 3. So this is level 2. And you can see this vertex raised a little higher than these two. That doesn't harm anything, as long as we don't push it up so that it is the same height as these sets, as these vertices. And it gives us a little better perspective on what the Hasse diagram looks like. And so we have these 3 lines, 3 edges, indicating the covering relation. Next come the doubleton subsets and the lines that are required to indicate the covering relationship. And finally, the whole set and the 3 lines required to indicate the covering. So the edges of this diagram show the covering relation, not the full relation. The set containing 3 is contained in the full set. There's no line between the two because we're only putting a line where there's a covering. So to get from this set to the full set, we pass through one or the other of these two doubleton sets. So you can still read the full relation, in this case the subset relation, from the Hasse diagram. But if you added all the lines for one subset being contained in another, it would be unreadable. So by only drawing lines or edges for the covering relation, you get a nice picture, gives you all the information, and this is a nice little cube. Okay. How's a diagram for this set under divisibility? 1 is at the first level. Nothing divides 1 but itself. These are the primes, 2 and 3. 9 covers 3. 6 covers 3. 6 covers 2. 4 covers 2. 8 covers 4. So that's the diagram. Okay, one last idea here. If we have a post set, P with a less than or equal to relation, and S is a non-empty subset of P, I think I talked about this before, then the order relation on P can be restricted to S. All you do is say, I'm only going to talk about the elements of S and their order relationship. The order relation restricted to S is still reflexive, antisymmetric, and transitive. Those properties hold for all the elements of P, therefore they hold for just the elements of S. So we get a new poset. Same order relation but restricted to the subset S. And we say then that S inherits the order from P. You could no doubt define a different order relation on S. That would have nothing to do then with the original poset on P. So we're just talking about inheriting the same order relation. So for example, Z, the integers, inherits the order relation, the usual relation, from R, the real numbers. Now here's the key concept. If P is a partially ordered set and S is a subset of P with the inherited order, and if the inherited order on S, the subset, turns out to be a total order, then S is referred to as a chain in P. This is a very important concept in the study of partial orders. So for example, let's take this set P under divisibility. Okay, this is not totally ordered. Okay. 3 and 8, for example, are not related. 3 does not divide 8, 8 does not divide 3. This subset, 2, 4, 8, is totally ordered under the same divisibility. Therefore, it is referred to as a chain in P, because 2 divides 4, which divides 8. 2, 3, 4 is a poset under divisibility. It inherits divisibility from P, but it's not a chain because 2 and 3 are incomparable under divisibility. Okay. So S2 is not totally ordered. Okay, I think that will do it for this video. Let's take a look here. Coming up next, more on partially ordered sets, maximal and minimal elements. Very important concepts in the theory of partial orders, which incidentally sort of disappear when you're talking about totally ordered sets. So these two concepts, maximal and minimal, are, let's say, significant only for partially ordered sets that are not totally ordered. So there'll be new concepts to you if you have not studied partial order before. Topological sorting is something that's very important in certain areas of application, such as computer science. So we'll go into that in the next video. Thank you for watching. Hope to see you in the next video.